Let's talk about the gap between what AI benchmarks claim and what actually happens when you use an AI in the real world. If you've ever given an LLM a vague prompt like, "Find me a good gift for my kid," or "Set up a project that trains a classifier," you've experienced the problem this research tackles. Current benchmarks evaluate models on fully specified tasks. You get the exact goal, the exact constraints, and the exact success criteria. The model just executes. But real users almost never start with complete specifications. Our goals are incomplete, exploratory, ambiguous, and they evolve as we talk. This creates a critical bottleneck. The model isn't failing because it can't execute a known task. It's failing because it can't figure out which task you actually intend. Researchers at Stanford have formalized this problem as task alignment. They've built a domain general framework to measure how well models align with users on underspecified tasks, and they've formalized the entire interaction as a partially observable Markov decision process, or POMDP. Let's break down exactly how that works, what the data shows, and why this changes how we should evaluate AI agency. First, the framework. In a standard Markov decision process, the agent knows the exact state of the environment. Here, the state is hidden. The assistant only observes the conversation history. At any given turn, the true task specification is fixed, but the user's current intent is only partially revealed. The assistant must maintain a belief distribution over a candidate's set of possible tasks, update that belief as the conversation progresses, and decide when it has enough information to commit to execution. Formally, the POMDP is defined over states, observations, actions, transitions, and rewards. The state captures the ground truth specification, the user's evolving intent, and the dialogue history. The observation is just the conversation so far. The action space has three components: the natural language response, a binary stop signal that commits the model to execution, and a ranking over candidate tasks that we use purely for evaluation. The transition is driven by a user simulator. The simulator has privileged access to the ground truth task, but it only reveals information progressively. As the assistant asks questions or makes assumptions, the user's intent state evolves toward the final specification. This setup cleanly decouples task discovery from task execution, which is exactly what we need to isolate alignment as a distinct capability. Now, how do we measure whether the model is actually doing this well? The authors track two complementary dimensions. First, task recovery. This measures whether the assistant identifies the intended task by the time it commits. They use commit at 1, which is the percentage of times the ground truth task ranks first at the commit turn. They also track commit rank, a normalized score between 0 and 1, and a composite commit reward that balances accuracy against interaction cost. The reward function penalizes unnecessary turns, forcing the model to find the right task without dragging out the conversation. Second, uncertainty resolution. Ranking alone doesn't tell us if the model is actually using the conversation effectively. To measure this, they track belief entropy over the candidate set. After each turn, the model is asked to rank the candidates in a separate evaluation thread. The log probabilities are converted into a normalized belief distribution, and the entropy is calculated. The total information gain is simply the drop in entropy from the start of the conversation to the commit turn. This tells us whether the model is systematically narrowing down plausible tasks through useful interaction, or just guessing. They also introduce a 4-quadrant taxonomy at the commit turn that cross-references correctness with confidence. You can be confidently correct, lucky correct, confidently wrong, or honestly uncertain. This is crucial for understanding calibration. A model that guesses right, but has high entropy is behaving very differently from one that commits with low entropy and high confidence. So what happens when you run this framework across state-of-the-art models? They evaluated 14 models across 3 domains: online shopping, professional work deliverables, and command-line coding tasks. The results are consistent and revealing. Under abstract, underspecified user intent, models recover the correct task only between 22 and 32% of the time on average. Even after 15 turns of interaction, alignment remains a major bottleneck. The most striking behavioral signature is premature commitment. Models like the GPT-5-4 family commit to execution within 1 to 3 conversation turns, almost everywhere, regardless of the domain. They interact ineffectively, failing to clarify the task, and often land in the confidently wrong quadrant. Other models like QN take more turns to commit, but they still struggle to accurately track the latent intent. Scaling model size improves raw ranking, but it does not consistently improve confidence or calibration. In fact, larger models sometimes become more confidently wrong. Here's where the framework really shines. The authors test whether task alignment is just a byproduct of raw task capability. They use shopping as a capability-saturated control. All 14 models perform nearly identically on the underlying shopping benchmark, with scores clustered between 81 and 88%. Yet their alignment scores vary almost threefold. This proves that alignment is a separable, domain-general axis of model behavior. It's not just about being smart at the downstream task. It's about how the model navigates uncertainty before execution. They also show that alignment is stable across domains. Models that identify tasks well in shopping tend to do so in coding and professional work, even after controlling for capability. To understand why humans outperform models here, they ran a human-as-assistant study. Human participants interacted with the same user simulator and recovered the correct task 48% of the time, significantly beating the strongest LLMs. Then they ran a critical ablation. They fed the actual human conversation transcripts into the models and asked them to guess the task. The model's performance nearly doubled. This tells us the bottleneck isn't inference. It's communication. Humans are simply more effective at driving the interaction, asking targeted clarifying questions, and extracting information under ambiguity. Given this gap, can we train models to align better? The authors fine-tuned QN3, 5-9b using both supervised fine-tuning and reinforcement learning. The reward signal for RL was the commit reward, optimized with a group relative policy optimization algorithm. They trained on shopping tasks with abstract user intent. The results show clear progress. Both SFT and RL roughly doubled the commit reward over the base model. More importantly, the belief signature shifts dramatically. The trained models drastically reduce the confidently wrong quadrant, dropping from 53% down to around 19% under RL. They shift mass into the honestly uncertain quadrant, showing better calibration. They learn to ask more informative questions and delay commitment until entropy actually drops. But even after training, performance on human transcripts still falls short of actual human baselines. The framework successfully isolates the behavior, and post-training moves the needle, but we still haven't closed the gap. This research does something critical for the field. It moves evaluation past the illusion of fully specified benchmarks and forces us to measure how models handle the messy, incremental reality of human intent. Task alignment isn't a soft skill. It's a formal, measurable, and trainable capability. As models become more capable at execution, the primary bottleneck for reliable agency will shift to this exact problem: detecting ambiguity, eliciting information, and knowing when to act. Frameworks like this give us the tools to measure it, train for it, and ultimately build assistants that don't just guess what you want, but actually figure it out with you.